Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Fugacity from Volumetric Data Part 2. Since it is a continuation of previous lecture, we will be having a recapitulation of what we have discussed in previous lecture. In the previous class, we derived Fugacity coefficient from volumetric data information in the pressure explicit form or with temperature and volume as independent variables. Okay? Those Fugacity coefficient expressions we have derived for a component I of a mixture. We derived it as RT ln phi is equals to RT ln Fi by Yip is equals to integral V to infinity dou P by dou Ni at constant Tv Nj minus RT by V dV minus RT ln Z. This is what we have derived for a component I of a mixture. If that component is a pure component, then for a pure component I, we have derived it as RT ln Fi by P pure I is equals to integral V to infinity P by Ni minus RT by V dV minus RT ln Z plus RT Z minus 1, where Z is the compressibility factor of the system. It is given by PV by RT. Okay. So, now what we do? We take a few equations of state and then try to derive the Fugacity coefficient of a component I in a mixture as well as the Fugacity coefficient of a pure component I. Those things we will take now. So, Fugacity coefficient of a component in a mixture according to van der Waals equation. Consider a mixture whose volumetric properties are described by van der Waals equation given as P is equals to RT by V minus B minus A by V square. Now, here if the van der Waals equation is in this form, this equation we cannot write as a kind of volume explicit form, right. So, then we have to take the generalized Fugacity expressions in terms of pressure explicit form volumetric data whatever available. That means, from this equation we have to write in a pressure explicit form. Indeed, it is already given in a pressure explicit form. So, for this equation first we have to convert the molar volume into the total volume, and then we have to find out A, B constant for the mixtures, because A and B are the van der Waals constant and these are for the mixture because this equation is given for the mixture. So, those things we have to find out, and then we have to find out dou P by dou Ni and then substitute in equation number 53 of a previous lecture, that RT ln phi I is equals to integral dou P by dou Ni minus RT by V plus RT ln Z. That expression in that equation, in place of dou P by dou Ni, whatever dou P by dou Ni will get from this equation, that we have to substitute and simplify. Okay, that is what we are going to do now. Okay. First, convert this equation in terms of total volumes by replacing molar volume by total volume divided by the total number of moles Nt, and A and B are the van der Waals constant and they are dependent on the composition. That means, for pure gases they are experimentally available, A1, A2 etc., B1, B2 etc. are available. For pure components 1, 2 etc., right. So, when we mix them together 1, 2 etc. component, then obviously composition, different composition will give different gases mixture. So, for that mixture this A, B constant we have to obtain, and these A, B constants are functions of the composition of the mixture. Okay. So, those things also we have to see now. First part we will take only converting it in terms of a total volume, right. So, when we do this one by replacing small v by capital V by Nt and then simplifying, then we will have this equation, right. So, now we need dou P by dou Ni in order to substitute in equation number 53. Remember, for last couple of lectures and this lecture, equation numbers I am maintaining sequentially, so that it should not be confused. Okay. So, this first equation of this lecture is 60, okay, because in the until the previous lecture we had a equation number 59. Okay. So, now here dou P by dou Ni, this I am doing because all these last three, this lecture and then previous two lectures are connected one to other lecture one way or other way. So, that is the reason I am maintaining this equation number in a sequential manner for all three lectures. So, now for this equation of state in a pressure explicit form, what we will do? We will do dou P by dou Ni. That means, dou by dou Ni of this first term minus 1 by V square dou by dou Ni of A Nt square, right. So, here what is this A? This is we know that it is depends on the composition, alright. So, that means yi, yj etc. it depends. So, that means it is dependent on Ni. So, we have to differentiate this one, we cannot take it as a constant because it is dependent on the composition. So, what is that A for a mixture, that we do not know. So, for the time being we will not be able to differentiate this one. Similarly, same is true for B. So, now what we do, RT part of this differentiation is constant, because for all these calculations we are doing at constant temperature and composition. NT we have to differentiate with respect to Ni. Okay. So, differentiation of this one is here V minus NTB whole square, and then RT is constant, then V minus NTB dou by dou Ni of NT minus NT multiplied by dou by dou Ni of V minus NTB minus 1 by V square dou by dou Ni NT square A would be as it is. Now, if you dou by dou Ni is nothing but 1, and then dou by dou Ni of V minus NTB is nothing but 0 minus dou by dou Ni of NTB. This B also we do not know for the mixture, but it depends on the composition. So, it has to be evaluated once we find out what is that B depending on the composition. Same is true for the second term. So, that we are keeping as it is. So, further this we can simplify as RT by V minus NTB, and then this term NT RT dou by dou Ni NTB by V minus NTB whole square minus 1 by V square dou by dou Ni of NT square A is as it is. Now, this term will be substituting in equation number 53 here. This is the equation number 53. This is the equation for Figas-T of component I if the equation of state is given in a pressure explicit form, right. So, now here this dou P by dou Ni is nothing but this term, just we had minus RT by V is as it is, and then minus RT ln Z is as it is. Integration of this part is nothing but ln V minus NTB. Integration of this part is that is integral of 1 by V minus NTB whole square is nothing but minus 1 by V minus NTB, and then here also integral of 1 by V square is nothing but minus 1 by V, and then integral of 1 by V is nothing but ln V, right, and then these limits V to infinity are there anyway. Here we must remember this NT, B, A, NT, AB, NT etc. these R, T etc. are independent of volume. So, while doing the integration we can take them as a constant. Now, what we do, these two ln terms will join together, so that we can have this RT ln V minus NTB by V as one term, and then remaining terms we are keeping as it is without doing anything. Okay. Now, limiting condition we have to do this ln V minus NTB by V should be tending to 0 if V tends to infinity, because if you take ln the same thing you can write 1 minus NT B by V divided by 1, right. I am just taking V common from the numerator and denominator and cancelling out. So, now if V tends to infinity, so 1 by V should be tending to 0. So, ln of 1 by 1 is 0. So, that is what we get. Okay. So, other two limits 1 by V minus NTB should be tending to 0, and 1 by V should also be tending to 0 if V tends to infinity. When you substitute these limits, the previous expression reduces to this particular form. Okay. Okay. This here we have substituted only limiting conditions, whatever the V tends to some finite V and then V tends to infinity. Okay. Now, this equation is useful only when we know what is this dou by dou Ni of NT square A, and then we know dou by dou Ni of NTB. Then only this equation is useful, otherwise this equation is as good as nothing has been done. So, these equations we already understood, this B and A are dependent on the composition. So, we have to make some assumptions on how these A and B are dependent on the compositions, and these assumptions cannot be made based on the thermodynamic principles or thermodynamics understanding, but they can be made only based on the molecular considerations, right. So, what we do, we see a few mixing rules. Suppose m components in the mixture with spherical molecules, one can interpret B as follows, as cube root of B is sigma yi cube root of Bi. Now, this Bi is nothing but the that constant B of ith species if it is in pure form, okay, because this we know Ai, Bi etc. are available for pure when the gas and when the component is in pure form. Okay. So, for pure form they are available from experiments. So, if you wanted to know the mixture, so then we can use this as one of the mixing rule for B. There are many other mixing rules. If you take another mixing rule for B is like this, B is equals to sigma yi Bi, again Bi is for the that B constant for pure component I, and then yi is nothing but that particular composition of component I in the mixture. Okay. But it has been found by so many studies that whether we use this B expression or this expression, usually the results may not be affected much. Figastic calculations especially may not be affected much, especially at moderate densities. So, any of these two we can use. But what kind of mixing rule are you using for in order to find out the A constant for the mixture? It strongly influences the final results, especially Figastic results. So, one should be very careful while choosing mixing rule for A. So, if we interpret A as a term that reflects the strength of attraction between two molecules, indeed this A, out of these A and B constants, A is sometimes indicates the terms with A are indicating something like attractive forces, whereas the other terms with B terms etc., those indicating repulsive forces. Okay. So, for A this is one of the mixing rule, that is A is equals to sigma I is equals to 1 to m, sigma j is equals to 1 to m, yi, yj, aij, and then if I is not equals to j, then aij is nothing but square root of ij. If I is equals to j, then aij is nothing but ii, that is ai simply if I is equals to j or aj. If you write jj like kind of thing. Okay. So, now we use these mixing rules, and then further we simplify the equation that we have derived for Figastic coefficient in previous slide. Okay. So, then this is the actually previous equation 65 that we derived in previous equation. Now, we will be using some assumptions for NTB first. So, in place of B, we are using this sigma yi Bi mixing rule, okay, and then A, let us keep it as it is. Then these remaining terms, wherever these V terms, capital V terms are there, numerator and denominator I am dividing by NT, right, so that there will not be any change, and further in the next type wherever capital V by NT is there, I can write it as a molar volume small v. Okay. So, that is what I am doing here. Then, so this part now will become in terms of molar volume, that is small v by small v minus b, and then same here 1 by small v minus small b, and then here this sigma bi yi I can write ni by nt. So, nt and then this nt will be cancelled out, sigma bi ni would be there. Okay. This term we are keeping as it is. Further what I am doing, this RT, whatever RT is there, that I have already cancelled out from all the terms, right. Okay. So, that here we get 1 by VRT anyway, okay. That RT term has been brought to the right hand side. So, wherever that RT was there in the numerator, that has been cancelled out by denominator RT, wherever there was no RT. So, then this RT is coming in the denominator. Okay. Next, we know that dou by dou Ni of Bi Ni is nothing but Bi, okay. Bi by V minus B term is as it is, and we will be getting, and then remaining terms we are keeping as it is. Okay. So, now what we do in the next step, we try to find out this one. So, this one what we do for a binary component, right. For a binary component, mixing rule for A is nothing but y1 square A1 plus 2 y1 y2 square root of A1 A2 plus y2 square a2. y1 I am writing it for binary mixture is only y1 is the composition or mole fraction of component 1, y2 is mole fraction of component 2, a1 is constant A for pure component 1, a2 is constant A for pure component 2, right. Then dou by dou n1 of nt square A I am doing for first component in the binary mixture for simplicity. So, then this here wherever y1 is there I am writing n1 by nt, and then wherever y2 is there I am writing n2 by nt. So, then in place of A this is what I have. So, this nt square we can cancel out. Then if you differentiate from differentiation of the first term you will get 2 n1, a1 is constant, differentiation of second term I will get 2 n2 and then square root of a1 a2 is constant, and then third term is 0, differentiation of third term is 0. So, then from these two terms 2 square root of a1 I am taking common. So, then I can have n1 square root of a1 plus n2 square root of a2. The purpose of doing this differentiation for binary component is that now we can generalize this one to the multi-component mixture easily. This we can write for multi-component mixture as 2 square root of ai sigma j is equals to 1 to m nj square root of aj. So, this one we can substitute in the previous expression. Previous expression here what we had dou by dou ni of nt square a in this place and divided by v by rt was there. So, in place of dou by dou ni nt square a we are writing 2 square root of ai sigma j is equals to 1 to m nj square root of aj. So, now this term further next term what I am doing I am dividing by nt and I am both numerator and denominator I am dividing by nt. So, that nj by nt I can write it as yj, and then capital V by nt I can write it as small v molar volume. Rest all other terms we are keeping same without changing anything. So, this is the expression for Figasty component of I in a mixture if the mixture equation of state of the mixture is given in a pressure explicit form according to van der Waals equation of state, right, and then Z is nothing but compressibility of the mixture, that is nothing but PV by RT. Now, we take Redlich-Kwong equation as a kind of example. We take a pure component whose equation of state is described by Redlich-Kwong equation, and it is given by P is equals to RT by V minus B minus A by V plus B square root of T, where A and B are constants. So, these are for the pure components. So, it is a pure component. So, we do not need to worry about the mixture. So, we have to find out F pure I. So, that is integral P by Ni minus RT by V dV minus RT ln Z plus RT Z minus 1, that is what we have to find out. If in that equation P by Ni we have to find out what it is, and then what is P by Ni according to Redlich-Kwong equation we have to find out and substitute that equation in that equation. So, P first what I am doing I am writing I am dividing this equation both sides by Ni, okay, and then wherever this let us say first term, in this term I am doing RT by V minus B 1 by Ni is there. So, this one I can write RT molar volume into number of moles is nothing but total volume capital V minus B Ni. Similar rearrangement if I do for the second term, then I can get A Ni by capital V multiplied by capital V plus Nib square root of T. Okay. Now, this expression what I will be doing next step I will be separating 1 by V plus Nib in two terms, so that I can do integration easily, right. So, that I do A Ni by square root of T is constant, and then this term 1 by V plus Nib, if I write in two terms I can write it as 1 by V minus 1 by V plus Nib multiplied by 1 by Nib, which is same as 1 by V into V plus Nib, right. So, now this Ni I can cancel out, whereas the remaining terms are same. So, this is actually we need integral v to infinity p by Ni minus RT by v dv. So, p this term is p by Ni, this term is RT by v as it is, as a separate term I have written, right. Further, if you integrate this equation, now what will have? The integration of first term is nothing but RT ln v minus b Ni, because b and Ni are independent of v. So, we can treat them as constant while doing the integration. Similarly, integration of this part is ln v minus ln v plus Nib, and then integration of 1 by v is nothing but ln v, and then limits are v to infinity. So, v to infinity we substitute here, substitution we do later. Now, what we do? We combine these two terms as ln a minus ln b is equals to ln a by b form. So, ln v by v plus Nib we are having here, and then RT ln v is as it is. Now, in the next step what I have done, the first ln term and then last ln v term I have clubbed together as ln of v minus b Ni by v form, and then this term is as it is without any change. So, now RT ln v minus b Ni by v I can write by substituting this limits infinity, plus a by b square root of t ln v by v plus Nib. It should here it was minus, here it was plus. So, now it is reverse minus and plus, because upper limit when v tends to infinity, both these two terms are tending to 0. So, lower limits when v is equals to v, then we get the negative symbol here when substituting the limits. So, we have for RT ln f by p pure I, this expression we derived. So, in this place for Redlich-Kwong equation, what is integral p by Ni minus RT by v dv, that we just derived. So, that one is nothing but this one. Okay, just now we derived for Redlich-Kwong equation. For Redlich-Kwong equation, integral p by Ni minus RT by v dv is nothing but this one. Okay, and then remaining term minus RT ln z plus RT z minus 1 we are keeping as it is. So, this RT if I can cancel out, and then wherever these v terms are there, so both numerator and denominators I am dividing by nt, so that capital V by Ni or nt is same. Capital V by Ni I can write it as small v molar volume, here also the same thing, and then here also same thing. We do not get any additional terms, rather this multiplication whatever Ni's are there, they will be cancelled out, because we are dividing by Ni both numerator and denominators, right. So, now next step what we have to do, what is this z we have to find out, because this ln z plus z minus 1 whatever are these terms are there we can substitute. Z is nothing but PV by RT. So, a Redlich-Kwong equation if you rearrange in terms of PV by RT is equals to, then remaining terms would be V by V minus B minus A RT power 3 by 2 V plus B, this is what you get. Z minus 1 is nothing but this term minus 1. Okay. So, that if you do the LCM you will get B minus V minus B as first term, and then second term would be as it is, then ln z would be ln of V by V minus B minus A by RT power 3 by 2 V plus B, this is what you get. So, these two terms you can substitute here for these two cases. When you do this one, you will get z minus 1 is this one, and then ln z is this part. Remaining first two terms are as it is, we are not changing them. This is z minus 1 term, and this term is ln of z term, right. So, now what we do, this particular ln term and then this particular ln term, that is first and last ln terms, I am writing ln a minus ln b is equals to ln a by b form. So, then I get this particular term, and then remaining terms are as it is, right. Next step, this I can further simplify as 1 minus a RT power 3 by 2 V plus B V minus B by B, this is what I get by simplifying this particular term, right. Then we have equation of state given like this. I am further simplifying what is this, can we simplify further. So that it will be having less number of term, that is what I am doing. So, this equation, if I rearrange, this is the Redlich-Kwong equation of state for pure component, it is given. If I rearrange this equation, P multiplied by V minus B R T, then I will get this one as 1 minus A multiplied by V minus B divided by R T power 3 by 2 V plus B, which is nothing but this term, ln term. So, in place of ln of this term, I can write ln of P V minus B by R T. So, that I will be doing here in the next step. So, in place of that particular term, I am writing P V minus B by R T here. Now, what I do, last term of RHS I am taking to the left hand side, then I can have this ln of f by P pure I plus ln of P V minus B R T. So, ln of A plus ln of B is equals to ln of A multiplied by B form I can write. So, then I have written ln f by P multiplied by P V minus B R T, and then in the right hand side terms I am keeping as it is without any change. So, now I can take exponential by taking off ln, because I want expression for f pure I. So, then this is what I am having. That means f by P pure I can write it as R T by P V minus B exponential of this term as it is. Okay. So, now we have a final expression for Figure of pure component I if the equation of state is described by Redlich-Kwong equation, and then that is given in a pressure explicit form. Then the Figure of that pure component is nothing but this one. So, now we have taken two examples. One is like we take a mixture whose equation of state is described by Van der Waals equation. So, that equation we have written in a pressure explicit form, and then we found what is phi I expression for that component I in the mixture. Then we have taken a pure component, but the equation of state is Redlich-Kwong equation, and then that Redlich-Kwong equation is given in a pressure explicit form. For that case, what is the Figure of pure component I, that is f pure I, is this one. This is what we have derived. Okay, now what we have this V as function of temperature, pressure, and then composition, so and so. Then we have a certain expression for phi I and f pure I. This is what we derived in one of the previous lecture, and then this lecture we have this equation of state as a pressure explicit form as a function of temperature, volume, N1, N2, and composition, so and so. So, in the previous case, temperature and pressure are independent variables. So, there by keeping temperature constant, we could find out what is the effect of a change in pressure. What is the effect of change in pressure? That would be occurring in the phi I and in f pure I that we have seen. In today's lecture, temperature and volume as independent variables. So, at constant temperature, by changing the volume, how much change in the phi I and then f pure I occurring, those things we have seen in this particular lecture. Okay. Now, what we do, let us say you have one equation of state, and then you can write that one as a volume explicit form as well as the pressure explicit form, right. So, then both these equations will provide us the same phi I or f pure I or not, or different equation, that we have to cross check. Indeed, they have to provide the same expression, then only these derivations are correct. That generalized expression that we have derived for the Figure coefficient of component I or Figure of pure component I, they can be correct or reliable only when you take one equation of state, but that equation of state you write as a kind of volume explicit form and pressure explicit form, and then you derive corresponding Figure coefficients and then cross check. If you are getting same thing, then it they are correct, otherwise you might have made some kind of mistakes. That is what you would be realizing. Okay. That we cross check now. Whether volume explicit and pressure explicit forms give same expression for Figure or not, that is what we check. So, already in one of the previous lecture we have taken van der Waals equation in volume explicit form. Van der Waals expression is given by this PV is equals to RT plus B minus A by RT P, right, and then we found phi 1 we have taken for the binary component, binary mixture. So, phi 1 we found this equation 34 in lecture number 4, and then for F pure 1 we found this equation 35 in the same lecture number 4, right. From these two we derived F1 is equals to y1 F pure 1 exponential of square root of a1 minus square root of a2 whole square y2 square p by RT square. This is what we have derived. Now, the same equation of state we will write it in a pressure explicit form. Okay. So, this is these two 34, 35 and 36 these equations we got when we wrote this equation of state in a volume explicit form, but the same expression same same expression now we will write in a pressure explicit form like this, and then we will be using equation number 53 and 54 in order to get phi 1 and then F pure 1 and then check whether are we getting these expressions or not. If the equation of state is same and whether you are writing that equation of state is volume explicit form or pressure explicit form, you should get the same Figas-T expression, right. So, these things in 34, 35 we have anyway derived. Now, using the pressure explicit form of same equation of state we will be doing for what is ln phi 1, F pure 1 etc. those things we evaluate and then check. We should get same expression, otherwise we are making some mistakes either in derivation or applying the derivation here for these equations of state. Okay. So, this PV is equals to RT plus B minus A by RT, this expression if I write pressure explicit form, this is what I get. What I have done, this B minus A by RT P, that term I have taken to the left hand side and P I have taken common. Then I have done the LCM and then rearrange it, P is one side and all other terms other side. Also what I have done, in place of molar volume small v, I have written capital V by NT, right. For phi 1 I have to find out dou p by dou n1, because RT ln phi 1 is nothing but integral V to infinity dou p by dou n1 minus RT by V dV minus RT ln z. So, dou p by dou n1 we have to find out. So, this is the P in pressure explicit form. Van der Waals equation is this one. So, this one dou p by dou ni is simply d of x by y form. So, that if you do and then simplify, we get here this expression for dou p by dou n1. Okay. So, here RT whole square is a kind of constant term that I can take constant. So, NT by V minus B NT RT plus A NT, this one I have to differentiate. So, V minus B NT RT plus A NT whole square is as it is. Then this V minus B NT RT plus A NT RT square dou by dou n1 of NT is nothing but 1 minus NT RT square, and dou by dou n1 of V minus B n1 RT plus A NT is nothing but dou by dou n1 of V is 0, and then dou by dou n1 of B NT is we do not know, unless we use mixing rule we cannot find out what is B and what is A, and dou by dou n1 of A NT we are keeping as it is, because this A and B are dependent on the composition. So, we have to use the mixing rule. So, now this differentiation I am writing in two terms like this. Okay. Then we will be using dou by dou n of B and T as we are using this B, we have used this while using this pressure explicit form derivation. When we do mixing rules, we have to use same one as we have used for the volume explicit form. For the volume explicit form, B we have written as sigma B I y I. B I is nothing but constant B for a pure component I. Okay. So, like that B1 B2 you have to get for the pure components. Then you have to write B is equals to B1 Y1 plus B2 Y2, and then Y1 Y2 I am writing it as N1 by NT and N2 by NT. So, B NT is nothing but B1 N1 plus B2 N2. We are doing for the binary mixture, because same van der Waals equation when we have taken as a kind of a volume explicit form, we have done for a binary mixture as a starting point. So, dou by dou N1 of B N T is nothing but dou by dou N1 of N1 B1 plus N2 B2, which is nothing but B1 according to mixing rule that we have taken. Okay. So, similarly, dou by dou N1 of A and T, A we are using this, we have used A for the mixture is equals to A1 Y1 square plus 2 square root of A1 A2 Y1 Y2 plus A2 Y2 square we have to use, because the same mixing rule we have used when we have done the same problem using the volume explicit form. So, here also when you write Y1 is equals to N1 by Nt and then Y2 is equals to N2 by Nt, then we have this expression. So, that mixing rule for A if you use, this is what you get. So, now we are differentiating this particular thing. So, now what I can do, I can cancel out Nt and then square of Nt, and then when I differentiate denominator Nt square will be there, Nt and then differentiation of this term is 2 N1 A1 plus 2 N2 square root of A1 A2 plus 0 minus this A part whatever, and then differentiation of Nt with respect to N1 is 1. Okay. This part if I write it here 2 N1 A1 Nt by Nt square, I can write it as 2 N1 A1 by Nt. So, that is 2 Y1 A1, and then similarly for this term I can write it as 2 N2 square root of A1 A2 Nt divided by Nt square. So, this Nt and then square of this one is cancelled out. So, 2 Y2 square root of A1 A2 I can write, right, and then this term I will be writing, this is nothing but simply A Y1 square plus 2 Y1 Y2 square root of A1 A2 plus Y2 square A2, this is nothing but this one. So, this is nothing but A. Okay. So, that if I do, I get 2 Y1 A1 first term plus 2 Y2 square root of A1 A2 second term, and then third term minus A. So, minus A anyway we can write, we have to write in this form. So, next part what I am doing, I will be doing from all Y1 terms together, Y2 terms together I am writing here. So, first this term and this term, from these two terms A1 Y1 I have taken common, and then from these two terms I have taken 2 square root of A1 A2 Y2 as a common. Then I have this one. In the next step 2 minus Y1 I can write it as 1 plus Y2, because Y1 is nothing but 1 minus Y2, and then Y1 I can write 1 minus Y2, right. So, this 1 minus Y1 I can write Y2. So, in place of dou by dou N1 of A and T, you can write it as A1 minus square root of A1 minus square root of A2 whole square Y2 square. That if you write in that particular term, so this is what we will get. Okay. This is what we have for in place of dou p by dou Ni by substituting whatever this this particular term is nothing but dou by dou N1 of A N T, that is what we had now. Okay. And this particular term is nothing but dou by dou N1 of B N T. Then further if you rearrange these terms, so and then integrate like this, so then you will have integration of this term is nothing but ln of the same term, then integration of 1 by v is ln v, and then integration of this term is nothing but this particular same term, because all this B1, A1, A1, A2, Y2, B etc., except this particular term denominator term, in the numerator everything is constant, So, numerator is as it is, and then denominator is square term is there. So, minus 1 by whatever this v minus b n t plus a n t r t that we will be getting by integrating it. So, limits v to infinity we can substitute for all these three terms. When we substitute these limits, we will be having this particular form. Okay. Further, you can simplify by dividing the numerator and denominator of both the terms by Nt, so that capital V by Nt I can write small v, molar volumes. So, that is what we have done here. So, then this particular term integral dou p by dou Ni minus RT by V in that equation number 53, RT ln F1 by Y1 P is nothing but integral V to infinity dou p by dou Ni minus RT by V dV RT ln Z if it is pressure explicit form. If the equation of state is pressure explicit form, this one we just derived here. So, that we will be substituting here now. Then we substitute, you will get this particular term, and then RT ln Z as it is, ln Z I am writing PV by RT. So, we will have this term. So, first ln term and then last ln term I combined it as this term. Okay. So, this V minus B RT plus A I have written in red, because from equation of state PV is equals to RT plus B minus A by RT P, this is equation of state. If you rearrange this equation, then V minus B plus A by RT, you will be getting RT by P. That means V minus B RT plus A is nothing but RT whole square by P. So, wherever this red font V minus B RT plus A is there, there I can substitute RT square by P. When I substitute this one here, RT square by P in the denominator. So, then that I can write P by RT square. Here in also in the denominator RT square by P I have written. So, now what we can see, this is RT and then RT square cancel out, PV and then PV is cancelled out. So, ln of 1 is there. So, the first term is ln of 1 is 0 and then remaining term is like this. I am just writing first I am splitting it in two terms. So, this B1 RT minus A1 by RT square by P, that one term, and then remaining square root of A1 minus square root of A2 whole square Y2 square by RT square by P, that I am writing as a second term. That means ln F1 by Y1 P is equals to B1 minus A1 by RT, P by RT plus square root of A1 minus square root of A2 whole square Y2 square P by RT whole square. That means F1 is equals to Y1 P exponential of this term and then exponential of this term. And then this is, if you recollect, cross check, it is the same expression when we have used van der Waals equation as a kind of volume explicit form. Now, we have cross checked that the Figasty coefficient expression, generalized expressions are correct whether we use volume explicit form or pressure explicit form of equation of state, they will give the same answer for any equation of state. So, for a pure component I, if the equation of state is available in pressure explicit form, then what is the Figasty of pure component I for the van der Waals equation of state that we have taken? We have taken this van der Waals equation of state PV is equals to RT plus B minus A by RTP, right. So, for this equation of state, we have already written as a kind of volume explicit form, and then we obtain Figasty of that pure component I, right, and then we got that one as answer as F pure I is equals to P exponential of B minus A by RT P by RT. This is what we have already got it. So, but if the same equation of state, if I write it as a kind of pressure explicit form and then obtain the Figasty coefficient of that pure component I, am I getting the same thing or not? That is what cross checking we have done. We have already done for a component I in a mixture. Now, we are taking the same concept, same equation of state, but pure component. So, that to make sure whether the derivations are whether generalized Figasty coefficient expressions are correct, are they applicable for all for a given equation of state, whether I use volume explicit form or pressure explicit form, are they giving same answer or not, that is what we are verifying. So, for a component I in the mixture we have already done. So, for a pure component I we are doing for the equation of state given by van der Waals equation. So, now we need Z minus 1 somewhere in the generalized expression for Figasty of pure component I. So, that is Z is nothing but PV by RT. So, that I am writing PV by RT minus 1 from this equation is nothing but B minus A by RT, P by RT. Now, this equation of state, what I am doing? I am doing a kind of pressure explicit form. I have written like a pressure explicit form like this, and then I am dividing both sides by Ni, because I need integral P by Ni dV information in the, so that to substitute in generalized Figasti expression, right. So, then now here small v multiplied by Ni is nothing but capital V, that is total volume, and then minus Bni plus Ani by RT, this is what we are getting. So, we need integral P by Ni minus RT by V dV. So, P by Ni is this term minus RT by V. Here in this equation A, B, R are the constant, okay, and temperature also we are doing all these expressions at constant temperature and composition. So, they are independent of the volume. So, when we do the integration of these things, ln of this term and then ln of V, this term we will get, there is a RT multiplication and then limits V to infinity. Now, this is RT you can take common, and then it is in the form of ln A minus ln B. So, you can write ln A by B form and then substitute limits V to infinity, you will get RT ln V by V minus Bni plus Ani by RT. And now again this here within this inside this ln terms, now what I am doing, I am dividing both numerator and denominator by Ni, so that capital V by Ni I can write it as a small v, that is molar volume. Then I have this same equation RT ln V by V minus B plus A by RT, that I can write RT ln VRT by V minus B RT plus A. This expression we can substitute here in generalized expression for a Figasti coefficient of component I, pure component I. So, in place of integral P by Ni minus RT by V dV, whatever we got, we substitute here. Z also we have found, Z minus 1 also we have found. So, those things we substitute here, right. So, this is this particular term is nothing but integral P by Ni minus RT by V dV, just we derived, and then RT ln Z, Z we are writing PV by RT, and Z minus 1 we have seen from equation of state is nothing but B minus A by RT, P by RT. And from the same equation of state we have seen this V minus B RT plus A is nothing but R square T square by P. So, that we can substitute here, okay. And then this ln A minus ln B form is there, ln A by B form I can write. So, then VRT by R square T square by P divided by PV by RT is there. So, that I can write multiplied by RT by PV. So, here R square T square, here R square T square is cancelled out, here V cancelled out, and then this P will be cancelled out. So, that we have ln of 1, that is 0. So, only term is remaining is this term. That means ln Fi by P pure I is equals to B minus A by RT, P by RT, or F pure I is equals to P exponential of B minus A by RT, P by RT. So, now by taking pressure explicit form also, we got the pure component Figasti same as the one that we got by taking the equation of state in a volume explicit form and using corresponding Figasti relations, corresponding generalized Figasti relation, right. So, what does it mean? Whether you take equation of state volume explicit form or pressure explicit form, when you use the corresponding Figasti relations, generalized Figasti relations, then you will be getting the same answer, whether it is a component I in a mixture or whether it is a pure component I. So, that is in summary, if you have the equation of state in volume explicit form, then for a component I in the mixture you can use this equation. If the component is pure component I, then you can use this equation to get the Figasti of that pure component I. But if you have the equation of state in pressure explicit form, then for a component I in the mixture, you can use this equation to get the Figasti coefficient of component I in the mixture. And then if the component is pure component I, then you can use this last expression to get the Figasti of that particular component in a pure form. Okay. So, let us say whether that is whether you use this equation or you use this equation, you get the same answer. Sometimes what happens, equations of states are such a way that You can write either in a volume explicit form or in a pressure explicit form. Mostly most of the equations of state are available in pressure explicit form. So, it is more convenient to use this expression, right. Similarly, for pure components also, if you whether you use this equation or you use this equation, you will be getting same F pure I expression. Okay. The references for this lecture are given here. Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnich et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, Introduction to Chemical Engineering Thermodynamics by Smith et al. Most of the details of the today's lecture as well as the previous two lectures can be found from these two references. Thank you.